Swayam Prabha. Digital India. Educated India.
Good day and welcome to this class. We are going to continue talking about geotechnical reuse of waste, a topic which we started last time. Last time we looked at reuse of coal ash, reuse of tailings, reuse of tires, reuse of slag, and I hope that after the discussion, if a new material is offered to you, very often a person from the industry will come and say, sir, I have this white powder and I have a huge mound of it. Can you use it for X, Y or Z purpose? Mostly the industry guys will know whether it is hazardous or not. But the fact is that if a person from the industry says he has got a material which is not hazardous in his opinion, then you should be able to check its suitability for using in earthworks. The moment it is very fine, you have a problem because it's likely to be silt or clay sized, and normally plasticity will not be there in the fine particles. Why do we get plasticity in soils? Because of the net negative charge on the fine particles, and the net negative charge on the fine particles come on account of the manner in which the clay particles have been formed. In a process in the industry, these very fine particles may be mostly physical crushing or physical breaking down of grains into a very fine powdery range. So, there may be no net negative charge on the particles. So, they may be like rock dust, which may be in the clay size range, but when you try and classify a material which is in the clay size range, which is non-plastic, how would you classify it in soil mechanics term? I give you a material, I say 100% of this material is, what is the clay size range? Below 2 microns. So, 100% of this material is below 2 microns, but it is non-plastic. How will you classify this soil? Will you call it sand? Will you call it silt? Will you call it clay? What will you call it? You will go to your A chart, grain size distribution is done, 100% of the material is finer than 2 microns, and you will go to your chart and plasticity index is 0. So, how will you classify it? It is not clay of low plasticity because it is non-plastic. So, it is a non-plastic soil in clay size range. There is no word given for this soil which is there separately, but it is not clay, because the moment you say it is clay, you imply it has plasticity and you imply it has a liquid limit and plastic limit. You can call it non-plastic clay sized material, that is fine. Actually, it is silt in the clay size range. Actually, it will behave like silt, but it is in the clay size range. Anyways, so when you get a new material, you have to perform all the tests, chemical, physical, environmental impact, so that before you start working with it, you are able to say that this material will not degrade with time, this material will not harm the environment with time, it is workable as a soil like material, and it can be worked with the existing earth moving equipment. Today we are going to look at two new issues. Municipal solid waste goes to a landfill, and what kind of biodegradable content does municipal solid waste have? Anybody would like to recall from what we discussed in the beginning? It can be as high as what? and as low as what? Biodegradable content in municipal solid waste. So, I may not be wrong if I might say that biodegradable content can be from 35% to 75%. It's the rare municipal solid waste which will have 100% biodegradables, because something or the other must be mixed in it. And it is the rare municipal solid waste which will have less than 35% biodegradables, because municipal solid waste is primarily the material which is coming out from the rejects from the households and the residential areas and the fruit and vegetable markets and commercial centers and everything. So, in a sense, 35 to 75% biodegradables is what the waste has. Now, if I bury it for 20 years, one would expect this waste to stabilize, and the processes in landfill are anaerobic. So, anaerobic processes will decompose and degrade this waste. I am hoping that in 20 years it will have fully stabilized. Do you think it would have fully stabilized? And I am talking of it being in a waste dump which was open every year, it rains and water would go through it. So, one would tend to think that old waste, the biodegradables would have decomposed, whatever leachate had to come out would have come out, whatever gases had to come out would have come out, and the non-biodegradable matrix is what which will remain. So, the question is, can I use 20-year-old waste as soil? That is the question. So, one would go to a landfill and pick up waste which is 20 years old and see what it comprises of. And just to remember, other than those 35 to 75% biodegradables, what did we have? A good thumb rule always is that you have 1/3 is biodegradable, 1/3 are inerts, construction and demolition debris, silt from the drains and dusting, sweeping dust, that's 30. And 33% are others, plastics, cloth, wood, rubber, leather, whatever you want to say. This is a good thumb rule. And in different countries, different things will happen. In some countries, a lot of paper will come because there is no kabadiwala system. In India, there will be no paper because you have very efficient kabadiwala system. So, depending on the kind of recycling system you have, waste may have different compositions. So, over a period of time, we would like to see whether aged municipal solid waste becomes stable. If it has not become fully stable, is it almost stable, and can we use it? So, that is the objective. The other aspect we are going to discuss today is that there are several waste to energy plants which have come up across the world, more than 2,000 to be precise. Now, they burn the waste. So, you burn coal, what do you get? What is this ash in the coal? How much ash do you get in coal in India? If I burn 100 units of coal, how much ash will come out? We have got poor quality coal, 30 to 40% ash is there. What is this ash? Is it I burnt the carbon and it became ash? Unlikely. C plus O2 is CO2. So, what is this ash in the coal? Soil or rock. When the coal was formed, it was not formed by a pure industrial process that you will get pure coal. After all these trees and vegetation and everything which got compressed under time, soil must have fallen in it also. So, the original coal has a ash content of 30, 35, 40%, means it has soil, it has impurity, and that impurity is soil. You burn it, what remains? Some of the ash which is formed from the coal. But what is this ash? This ash is actually the silica which is embedded in the coal. So, out comes ash. Now, if I burn waste, what will come out? Out will come ash. If I burn wood, what will come out? Out will come ash. Maybe in wood the ash will be only 5 to 10%, because its silica will be in the matrix of the wood. It can't have 30, 40%, wood can't have 30% soil inside it, it would not live. So, you burn municipal solid waste, out comes ash. How much ash will come in? Depends on how much soil you sent in. So, in some countries they will burn something called mass burn, they will burn the waste totally, high ash will come out because entire waste was sent. In some countries they'll say segregated, they'll do some segregation and only sell the combustibles, low ash will come out. We will also look at that ash, can that be reused and what's happening in the world. These are really both cutting edge topics right at the front of developments in the last 5 to 7 years. So we are going to address geotechnical reuse of aged municipal solid waste. So the word that we are going to use is aged, which we get from landfills, and incinerated municipal solid ash from WTE plants. But just as an equivalence, please see the equivalence here. We are saying that maybe in 10 to 20 years, all the biodegradables have decomposed, and that is what the waste to energy plant is doing in an hour, depending on the retention time inside. That, what is it burning? It's burning the organics, na? It is not burning the soil. If it had paper, it will burn. If it had cloth, it will burn. If it had food waste, it will burn. If it had leaves, it will burn. And what is the landfill doing? Landfill is decomposing them over a period of 20 years by anaerobic processes. What will be decomposed? The same stuff that will burn, except that plastics will burn in the incinerator. Plastics will not get degraded in the landfill. So let's look at aged municipal solid waste. The question is 10 to 20 years old waste from MSW dumps similar to soil? Can it be used for earthworks in embankments, filling low-lying areas and as backfill? So does aged municipal solid waste have significant non-inert material? We said now, the material that we should have should be physically and chemically stable. So is the organic content high? If it is high, we have a problem. The question is, what is high? Is 1% high, is 10% high, or is 50% high? Does it have bad smell? Does it give out colored water? Does it leach out colored water? And does it leach out heavy metals or any other deleterious materials like sulfates, chlorides and other salts? So the methodology is we look at the literature, look at the case studies of use of aged municipal solid waste, and also look at the data emerging from India. This I have already said, the objective is to see whether bulk geotechnical applications of aged municipal solid waste in embankments and filling of low-lying areas is feasible. If you look at the literature, and I am talking about some data from California, some from Korea, and 3 from India. And typically the age of the waste, 60 years, 25 years, 4 to 12 years, 15 years, 15 years. Bulk of it, the waste is soil sized, please understand. So if I come from this side, passing 2 mm sieve, about 40%, passing 2 mm sieve, about 60 to 70%. Passing 8 mm sieve, 60 to 70%. So gravel downwards or coarse sand downwards, 60% of the material not reported. Passing 75 microns sieve is about 30%. So it means the others are more. Here some liquid limit and plastic limit has been reported by California, but not reported in the others. Maximum dry density, good high range, indicating more soil-like behavior, a little lower range. OMC, wide variations. So the question is how much biodegradable content? 60 years, 6 to 12. 6 to 12, 14, 9 to 20, 9 to 16. So what was 35 to 75 has come to about 10%. That's all I can say. Maybe 15, sometimes as low as 5%. So what is low, what is high? That's the only question. Which is your acceptance line? Currently the acceptance line of defining organic soils is 3%, maybe extendable to 5%. If we do a lot of research, maybe this is even more extendable to 7 to 10%. But we have to be cautious when we do that, because there are materials which are having more organic content. Their compressibility is low, but you can see fide ash, the only one which has been reported from Seoul, is from 12 to 35 degrees. You can be sure that 35 degrees is when the organic content is low and 12 is when the organic content is high. So organic content does play a role in reducing your angle of shearing resistance. So we'll see how this material has been used as we go forward, but in this study from Southern California, they said, because you see, how do you bring this down to the acceptable level of 5%? Well, at California they said, if you want to use it, you will blend it with soil. It's like, you know, dilution. You mix soil with 6% organic content to 100 grams and take another 100 grams of soil with 0 organic content, mix the two, and the organic content will fall to 3%, and you can say, I can use this soil. So that's what they suggested. And they were very clear that if you are having organic content more than 8%, the soil behaves very badly. And of course, this is other materials. So some of the work done by some of our students here, including Mohit and Garima, is basically what's happening in India. So they have taken Mohit's work mainly, they've taken material from Kadapa landfill, which is in Andhra Pradesh, waste as old as 40 to 50 years. I mean, that's the oldest waste. It worked from 1970 to 2014. From Hyderabad landfill, started in 2001, so 15 to 17 years. Do remember, 15 to 17 years will be at the dead center. Getting to that waste and taking it out is not that simple. You get it? The landfill keeps on going like that. So what's the oldest waste is in the center. And then there's a Delhi landfill, which is started in 94 and age is about 10 to 22 years. So here's the kind of activity which one does. This is at Kadapa is a good site because that's a World Bank headed project where they are doing landfill mining. So if you set up a landfill mining, because they had dug up everything and mined it, you were not sure exactly what is the age of the waste because everything is now mixed. But in Hyderabad and in Delhi, one could get samples 8 to 10 years old and 10 to 20 years old. So here's the Kadapa operation. The material excavator is excavating it from the landfill. You use a trommel. A trommel is nothing but round screens with holes in it, and they rotate. So a trommel is a rotating screen, cylindrical rotating screen. What is the advantage? The soil keeps on dropping. Some of the soil will pass through and the other will go up and drop. As it drops, it breaks itself and passes through. So these are not like a grain size distribution. So here is a conveyor belt which takes the material up, and here is the screen through which the material passes through. So that this excavator will put the material in this pit, and this is the conveyor belt which is coming out of the pit. And as it goes up, these people are removing the large size material, can you see? And this is the large size material which is collected. They don't allow it to go to the screen, it will damage the screen. But this is the kind of material which comes out. Once it goes up the screen, these are the rotating screens. Okay, so this is the material that will fall out. This looks like soil, right? So some will fall out here, some will fall out here, and some will come out completely. And what comes out completely is the oversize fraction. So here you can see the oversize fraction falling here. So this is falling from here. This is the oversize fraction. This is the soil. This is soil-like. This is more sand gravel-like, and this is the oversize fraction, plastics and cloth and so on and so forth. So that's the soil-like material. That is the oversize fraction, and that's the landfill mining operation. Okay. But at the same site, which is now closed since 2004, 2014, 2004, 2014, you will still get dark colored liquid out. It's not operational. There's no fresh waste coming out. This is leachate. This is leachate. So that's an indication that some colored liquid is still coming out. It doesn't come out by itself. When it rains, it seeps through and comes out at the bottom. But this is what was done at Hyderabad. Here you can see a young man, we are all familiar with, digging out the old waste. This is what it looks like. And taking leachate samples, then coming into the trommel. This is the excavator bringing it, dumping it. That's the type of soil. In one location you get dark, in another case fresh brown soil. So now which has got more organic content? The light colored soil or the darker soil? The darker soil. Good. And this is at Delhi landfill, excavator being used. You can see this dark material, this is another material. And here there were no trommels, so these sieves have been made specially. Soil is put on it, and this is something, and this is something. Okay. And Mohit was able to retract the dates from the newspaper cuttings which were still there, and he could prove it that this was in 98. So that's almost 20 years ago. So he could. Anyways, so when you look at the material in terms of its compositional individual components, most of the material is soil size ranged. This is the oversized range. This is the big, large construction and when you say inert, you mean the large sized material. But you have plastics here in Kadapa, you have plastics and you have plastics. And there are others, a little bit of textiles, cloth rags, leather, wood, all these are burnable. These are energy recovery materials, please remember. When I do grain size distribution, I am interested in how much is soil-like material. Soil-like means gravel, sand, silt, clay. So sand range is less than 4.75 mm and gravel is 4.75 to 20, probably fine gravel, but there is also coarse gravel. So in any ways, here is the material which is less than 4, 20%, 20%, 16%. Here is the material which is 8 to 4. If you go up to 30, then it's 33 plus 12 plus 22. So about 60% material is soil-like. Okay? So this is from Kadapa. 60% material is soil-like. From Delhi also, if I go 35 down, 14, 35 to 16, 16 to 4, 4 to 0. 14 plus 20, 34 plus 33. 67, 10, 30, 70. So 60 to 70% material is in the soil sized range. Then let's look at organic content, because that's something which is important to us. So from 20-year-old Delhi landfill, 12 years old Delhi landfill, we are having 6 to 10%. But this is only the very fine range, please see. The wood fragments and the other will not go. The moment you go to a higher range, it goes up. Okay. Hyderabad landfill 11 to 12 in the very fine range, but if you go to the higher range, 20%. Kadapa landfill 6 to 7 to 7. But if I take Yamuna sand, 0.6, if I take Delhi silt, 1. They are less than 3%, and these are all above 3%. And still the full has to be done, because this matrix has only been done in this side. When you fill these up, maybe the values will go up, because this is only 20% of the material. If you are only going to take out 20% of the material, you are not going to be able to use much of the material. But when you mix water with them, because you saw black leachate at the site, you said let's mix water with the soil, so we get these kind of suspensions. And when you decant it through filter paper, this is silt, this is Delhi, this is Kadapa, this is Hyderabad. So there is some color which is coming out. And the other thing is the leachate that you analyze, they don't have very high heavy metals, maybe 1 or 2 exceeding the limits, but there are a lot of total dissolved salts. So we just mixed up 1:3 dilution or 1:4 dilution. This is just initial works, and we are getting very high values of total dissolved. Please see, Delhi silt is 100 to 200. In drinking water, 600 is acceptable, desirable, but here these are all in thousands. So that's a problem. And does it smell bad? When you excavate, it smells very bad. But within a month, there is very little odor. After aeration for a month, it's like soil. You feel it's like soil. High odor when you excavate it. And if you look at the permittable organic contents in the various literature, this is about up to 5% is allowed. Maybe sometimes 7% is also mentioned, but 5% is allowed. Then you look at case studies that all these landfill mining projects, how much of the soil has been used as an earth fill, and this is all these landfills abroad. And you are using about 60 to 70% soil. But all of them are reusing it at the landfill as intermediate cover, daily cover, intermediate cover, daily cover, cover. Nobody is using it as an earth fill, except one place it is written, but the details are not mentioned. So even today, because of the organic content and associated salts, there is a slight thinking that it cannot be used. But one thing is clear, maybe it requires some pre-treatment. And if I can find a cost-effective way of pre-treatment, then I can use it in the earthworks. If you look at the heavy metal concentrations reported in literature with respect to aged municipal solid waste, and if we compare these concentrations with respect to some standard levels reported from the Canadian standards, the Dutch standards, and also the continental crust, we find that in some of the aged waste, the heavy metals are higher or elevated. For example, if you look at chromium, then the screening level as per Canadian standards is 64 and the continental crust value is 25, but we are seeing that at least in 3 landfills the chromium values are more than these values. Similarly, copper, lead and cadmium have also been reported to be higher than the acceptable values, or at least elevated in comparison to the soil. We look at metal concentrations in aged municipal solid waste from Indian landfills, and here also we are using the Canadian standards and the Dutch standards along with the continental crust values. And if you look at this table where we have determined all these heavy metals, we find that in bulk of the landfills the chromium is high. In some of the landfills copper is at an elevated level, and in one of the landfills cadmium is at an elevated level. It's interesting to see that the Okhla landfill at Delhi, what are the heavy metal concentrations in comparison to the local soil adjacent to the Okhla landfill. And if I compare, you will see cadmium is similar, but nickel is higher, lead is higher, copper is higher, chromium is 10 times higher, zinc is elevated, manganese is elevated, and so is iron. So the issue is that in aged municipal solid waste, sometimes the heavy metals can be higher. This is another interesting comparison. We are looking at the heavy metals at Okhla, Hyderabad and Kadapa, and we are comparing this with the compost standards. That means, can the waste that we have taken out from these landfills, how do the heavy metals compare with the compost standards as per Indian MSW rules? And we find that if you look at cadmium, it is higher in Hyderabad and Kadapa. If you look at chromium, the acceptable value is 50, but in all the 3 aged waste it is higher, and so is copper in 2 of the landfills. So in this way, what we see is that in some landfills the heavy metals may be within limits, but in other landfills heavy metals may be at an elevated level. So use of aged municipal solid waste has been basically as cover and intermediate cover in most cases, and as earthworks it's not been widely reported. The issues about organic content, because aged waste is reported to have 6 to 20%. In some of the studies, heavy metals have been reported within limits. Often they will say they are higher, but issues about color and total dissolved solids have still to be resolved. But I do expect over the next 5 years that technologies will now be there where we can start reusing it. We do some aeration, we do some burning, we do some pre-treatment to make it workable. Any thoughts on your mind before we go forward? Because the next one is incinerated ash. So as far as aged municipal solid waste is concerned, one thing that does come out is it degrades very rapidly. In 10 years that 35-40% is down to 10-12%. And whether that limit of 5 can be taken to 10 is, the jury is still out. But remember that if you want to use more and more of the waste, you have to take the higher fractions. So as you go to coarser fractions, the organic content seems to be going up. So if you want to use 70%, then you have to use 30 mm down. And the test for doing organic content is a muffle furnace test, where the crucible in which you put the sample is very small. So if you want to take a lot of soil, then you have to have a big muffle furnace which is required for a representative organic content. Any questions? Okay. Then let's look at some data on waste to energy ash. So one of the thoughts which one has is that if you take the waste and burn it, it will vanish. So let me remind you, nothing vanishes. If you do mass burning in India and abroad, a lot of mass burn incinerators are there. That means they put everything in it, including the soil mixed, a little bit of pre-segregation, but you mass burn the whole thing. 30% to 35% of the material is still going to come out as ash, because that's the amount of soil and inerts which were there originally. So nothing vanishes. Volume reduction is 90% because plastics and paper and cloth will burn and wood will burn. So volume reduction is 90%, but weight reduction is only 70%. So we have 3 waste to energy plants in Delhi, but one has been working for the last 3 to 4 years. Other 2 have just started this year, so we will not look at the data from there. We've looked at the waste reaching the landfill from this one plant, and we also looked at data. Garima has done this literature as to what's the data regarding this ash. So there are more than 2,000 waste to energy plants which are burning 300 million tons of municipal solid waste every year, and they produce 60 to 90 million tons of ash. And this ash has also to be used, or it will go into landfills. In India, 5 plants are now operational or they have just started. Under the Swachh Bharat mission, 48 more are likely to come up in the near future. That's a huge number of waste to energy plants. But I do expect in all the major cities, in the 1 million plus cities, which is what 53 cities are all about, because we have no land, and the next city or the next village will not allow you to dump the waste near their backyard, we are going to have to use these waste to energy plants. Volume reduction is 90%, weight reduction is 70 to 80%. Do you remember in coal-fired boilers how much was bottom ash and how much was fly ash? In our coal-fired thermal power plants, when you did the, does anybody remember what percentage of the ash which comes out in coal plants is fly ash and what is bottom ash? Well, it was 20% bottom ash and 80% fly ash. So 80% of the ash is fly ash. Here it is opposite. 80 to 90% of the ash is bottom ash, and 10 to 20% is fly ash. Okay? So that's a big difference, number one. So when you look at literature, bottom ash is sand to gravel size, very good, can be of great use to us. Fly ash is basically sandy silt, silty sand. So it's a much finer material. Both are non-plastic, and their angle of shearing resistance is in the same range as soils. 30, 35, 40, 45 sands and gravels. But the problem is fly ash has leachable heavy metals. That's clear. That's a clear message coming out. In coal ash, it is still not 100% clear that all fly ashes have leachable heavy metals, though America is now saying that from the ash ponds some unusual heavy metals are leaching out. But here in MSW ash, in the fly ash, which is a low percentage, that means the metals get volatilized in the furnace, they go with the flue gases, and when the flue gases are caught with the ash, they deposit themselves on the fly ash. Bottom ash can be used in geotechnical applications, but sometimes has leachable salts, and therefore you may need some treatment or dosing of the bottom ash for earthworks. But the bulk of the cases, bottom ash is reusable with some nominal pre-treatment. Now the ash quality depends on the type of waste, how much inerts you are sending in, the type of incinerator, what is the process, what is the operating temperature. You are expected to be above 800 to 900 degrees centigrade in all these, so that dioxins are not created, and what are the types of additives that have been used in the processes of burning. So if you look at what's happening in Delhi Ash is coming in the form of in trucks. We are not sure whether it is mixed or unmixed, but no separate truck comes for fly ash and bottom ash, so maybe it's mixed. Maybe 8 trucks will be of bottom ash and 2 will be of fly ash. The ash doesn't look like coal ash, it's dark, it's not like the light grey fly ash that you saw, and you can see large sized particles because it's a mass burn of plant. And when you stockpile it, this one truckload, you can see some of the large sized stones. You could sample it using a loader, and this is the material which has reached the sieving station, and this is after drying. And now you can use the sieves of different sizes. These are sieving operations going on. So that is less than 4 mm, looks like soil, sandy material, comfortable, greyish, Yamuna sand like. That's 4 to 16 mm, but you see some non-soil like material. So everything doesn't seem to have burnt, right? We would expect at 900 this would have burnt. But anyway, still it's gravelly material, what we expected. That's 16 to 35. So mostly gravelly material, C&D waste, aggregate, some ceramics, some glass. So this should have burnt. And that's 35 to 80. Cloth, you can see, a lot of cloth. Okay, and of course large size material. And not to miss this, greater than 80 mm. 80 mm, 8 centimeters, 3 inches, the size of your triaxial sample, that's the sieve size. A lot of cloth and plastics, but some bricks and other materials as well. So if you look at the grain size distribution, 90% in the gravel to sand silt size range, 93%, 92%, 86%. If you look at the compositional analysis of the incinerator bottom ash from 2 waste to energy plants in Delhi, we see that the soil-like material is 90% of the total, and the other minor components are metal, glass, ceramics, some unburnt organics, and C&D waste. If you look at the data reported in literature on loss of ignition in the muffle furnace, then in the incinerated ash, the LOI can be as low as 2%, but it can be as high as 15%. That means all the organics are not completely burnt in the incineration process. Some values are now coming in from the 2 waste to energy plants in Delhi, and what we observe is that the LOI can be as low as 0.9%, but can be as high as 8.1%. This also seems to be dependent on the weather conditions during the cold months, the winter months like in February. Burning of the organics may not be as efficient, whereas in the summer months, let's say June, the burning of the organics may be more efficient. In comparison to the local soil of Delhi, which is Yamuna sand, you find that Yamuna sand has much lower loss on ignition and organic content. And similarly, in the ash which is coming from a local thermal power station in Delhi, the organic content of the loss on ignition at this site was much lower. The other issue regarding incinerated ash is the presence of heavy metals and soluble salts. So if you look at data emanating from different countries, fly ash has more abundance of heavy metals, and lead, zinc, cadmium, chromium have been the metals of concern. Whereas in bottom ash, it's more the salts. So there has been reporting of a high amount of chlorides and sulfates in many bottom ash samples, and heavy metals have not always reported have not always been reported to be of very high values, but we do see copper coming up again and again. If we look at the total dissolved solids data just emanating from the bottom ash of the 2 waste energy plants in Delhi, we find that the values are extremely high in comparison to the local Yamuna sand and the local bottom ash of a coal-fired thermal power station. If one looks at case studies for reutilization of incinerated bottom ash, we find that often it has been used for production of secondary aggregates or as part of the base course in road construction. 2 examples of embankment construction in Netherlands reported in the 80s talk about large utilization of bottom ash, but it's important to note that wherever bottom ash was used, a compacted clay liner was put over it and also a sand drainage layer in an attempt to keep the water out of the bottom ash which had been placed in the embankment, and groundwater quality was measured intensively on both sides of the embankment. And so is the case in the second example, where a sand bentonite mixture was used on top to minimize the infiltration of the rainwater reaching the bottom ash. In the other examples, bottom ash has been used within the landfill for construction of access roads, and also as a 30% substitute in aggregate for the asphalt access road in the US. So these are some examples of how MSW bottom ash after incineration has been used in different applications in roads and embankments. Well, that's all the testing that's been done so far. Data emanating from the world is that bottom ash in many cases can be utilized in geotechnical applications. So this is a front running area because you have 30% of the material which has to be taken care of. Landfills may become 1/3 their size, but they are not going to vanish. If you can take all this 1/3 material which is coming out in ash and put it in building blocks, put it in the building materials, put it in the roads, the inert matrix of life, if everything is burnt off, and put it in earthworks, then you can vanish the landfill. Then the landfill will vanish. Is that right? But you can't hide it. If it has got heavy metals, you have to report it. You can't just say, okay, I'll take a little bit and I will spread it over all over the area and I'll make the landfill vanish. So that's the information about geotechnical reuse of incinerated ash and aged municipal solid waste. I hope one of you will be working in this area in the future to solve the countries so that all the lovely mountains that we have of waste disappear in the future. So I'll be happy to answer any questions if you have something which bothers you or something, some alternate thought as to what we should do with all this. But quite clearly, once you do the sieving and the fractionation, it's clear that the soil-like fraction is towards the finer size, and the larger size material you can actually pick out the boulders. It can be treated like construction and demolition waste, and the balance of it can go into producing energy. That means all these cloths and plastics and paper can be re-sent back. But for that you have to do all this sieving again, and that is something which costs money. And
is there a better way of quantifying the plastics and the paper? So because when I see I have 60 nm log, so I see that the plastics and the paper might have just on one side they are long and on the other side they are small. They can pass through that sieve.
yeah, so this issue about sieving is an equivalent size, remember. So if you have a laminated, if you have a laminar element, that is a plane-like element, then you can always say that the smaller dimension can pass through, but the longer dimension may not. But it's like an equivalent overall thing. So the thing is, once you have sieved it, then you can only do compositional analysis, which is visual. I mean, you've sieved it, you got the big particles. Now keep the cloth, weigh it separately, keep the stone, weigh it separately, and keep the plastics and weigh it separately. And do remember that cloth and plastics look like too much. but their weight is very little. So in that large sized material that you're going to have, bulk of it will be the weight of the brick bats and the stones, and very little weight is going to be there of the plastics and the cloth, 1% or 2% only of the entire material. So compositional analysis has to be done, and I'm saying if this material goes into the geotechnical application, then over a period of time it is going to degrade. So we have to be very careful what is the organic content of the finer fraction, where visually you cannot. You see, once you have sand sized material, you can look at the sand grains, but you can't visually look at the pore size of the sand and say, no, this has got fiber, this has got wood pieces. So that will come out from the organic content. Any other thought which comes to your mind? But as earth becomes more and more expensive, remember local soil used to be 50 rupees per cubic meter several years ago, then it became 150, then it has become 500 now. So as local soil becomes 500 rupees per cubic meter or even more, the economics of reusing these materials after sieving, what it says is, if you've got ash, the cost of sieving, sending in a truck, fractionating, putting it in a truck, bringing it to site must be cheaper than the cost of digging up soil from nearby area. So as these two will come on par sooner or later. All you have to do is underwrite it will not pollute the soil and the environment around it. It should not smell bad. There should be no colored water coming out of it. We haven't done the colored water test on this. We could also check that out, and there should be no salts which should be coming out in a big way. So we'll stop here. Have a good day.